I would like to thank Amanda for the kind introduction and Axel Müller, the organizers of the International Medieval Congress in Leeds, for the invitation to give this lecture. The fight against global warming has become a crusade, at least in the campaigns of some of its proponents. Individual climate crusaders such as Alexander Zastara, who does great work with school kids in the Miami Beach area, even created new symbols and tunics for the struggle against carbon dioxide. Scholars of the medieval crusades may be perplexed by the appeal the concept still has despite its rather ambivalent, to say the least, assessment in modern historiography. The term crusade, however, equally opens a flank for attacks of climate change deniers, who depict Greta Thunberg sneeringly as new Joan of Arc abused by sinister globalist circles, or the Fridays for Future movement as a misguided children's crusade. The same groups, though, tend to interpret the Middle Ages as a period of the rise of the European civilization, fostered by climatic conditions of the so-called medieval warm period. This serves their agenda in two ways. First, to demonstrate that the scale of modern-day global warming is not exceptional in comparison with the medieval one, and can be explained by natural fluctuations in the same way as the medieval one, and second, to argue that warm periods in general are beneficial for human societies as they assume the medieval one generally was. To support these assumptions with evidence, even crowdfunding campaigns for critical research are established as the one on the German Die Kalte Sonne website. This initiative and others like the European Institute for Climate and Energy equally use graphs, such as the one to the left, to illustrate that earlier warm periods equaled or even excelled modern-day global warming. One finds the same graph on the website of the US climate change skeptic Steve Gorham. In her excellent book on a genealogy of global image politics of climate and climate change, Birgit Schneider has analyzed the various ways by which images are used and abused in the debate on global warming. She demonstrates how deniers of anthropogenic climate change manipulate these graphs to obscure the actual rate and scale of the rise of global temperatures in the last decades, by cutting off the curve at an earlier point in time, for instance. The misuse of this graph was partly facilitated by a misinterpretation of an image created by the intellectual father of the medieval warm period, Hubert Lamb. This pioneer of modern historical climatology introduced the term in 1959 based on a reading of medieval sources and the then limited number of temperature reconstructions for England. In 1964, using the same data, he published this graph with the caption "Temperatures prevailing in central England 50 years averages," indicating that it represented rather rough estimates. Nevertheless, the suggestive power of the image, showing an impressive temperature amount of medieval warm period, by far outperforming modern-day global warming, proved more powerful than the caveats of Lamb. Things got even more confusing when the Intergovernmental Panel on Climate Change, the IPCC, in its first assessment report in 1990, used Lamb's graph for central England with the misleading caption "schematic diagrams of global temperature variations since the last 1,000 years." This mistake was repaired in all following IPCC assessment reports since 1996, which presented much more refined and global and not English temperature reconstructions. They illustrate that the scale and rate of modern-day global warming significantly excels the medieval one. Furthermore, the IPCC reports demonstrate that modern-day climate dynamics, in contrast to those in medieval times, cannot be explained by natural forcing alone. This would be the blue line on the graph bottom right, but mainly emerge from the impact of human activities. Skeptics and deniers of anthropogenic climate change, however, remain unconvinced and prefer to use the now outdated Lamb IPCC graph of 1990, for instance. Their simplifying narrative is also easier to sell than the ones that the IPCC and historical climatologists tell. Their stories, with the refinement of methods and data, got more and more complex. As this 2005 graph of reconstructed Northern Hemisphere winter temperatures for the period 200 to 2000 CE shows, the smooth trajectories of LAMP were replaced by a multitude of fluctuations. Only the dotted average trend line indicates some more pronounced transitions which can be used for general periodization, as it is still found in many publications. A Roman climate optimum, followed by a late antique cold period, which, maybe in the 9th century, gave way to a medieval warm period, which in the late 1200s ended in an incipient Little Ice Age. Yet even Wikipedia now identifies the medieval warm period and the Little Ice Age as heterogeneous concepts with competing chronologies offered in scholarship. A main cause for this development is the impressive increase of the amount of data since Hubert Lamb drew his graph in the 1960s. As this map for parts of Europe and the Mediterranean indicates, instrumental measurements of precipitation, temperature, or air pressure, especially in a systematic way, in most regions did not start before the late 19th or early 20th century. For earlier periods, scholars have to rely on two types of archives, as the Swiss pioneer of historical climatology, Christian Pfister, has called them. The first are archives of society, mainly those types of written sources historians are well acquainted with. They provide either direct observations on meteorological phenomena or indirect ones on organic phenomena connected to the dynamics of temperature or precipitation, such as the starting date of the blooming of plants. In rare cases, they provide quantitative measurements, such as records of the water level of the annual Nile floods, which exist in continuous time series from 622 CE onwards. Indirect observations, if existence in continuous form, can also be used as proxies for climatic parameters, such as the starting dates of cherry blossom in Kyoto in Japan. They allow for a reconstruction of spring temperatures in the region since the 9th century CE, and thus for a long-term comparison of the current temperature trends, which in 2021 resulted in the earliest cherry blossom season ever recorded in the last 1,200 years. As all types of written evidence, however, the archives of society are highly unequally distributed across time and space. Thus, as these maps demonstrate, we are much better informed about weather phenomena in and around Constantinople than for other regions of the Byzantine Empire, for instance, and know much more about extreme events in Baghdad, Damascus, Cairo, or Mecca than in other areas of the medieval Islamic world. The most significant increase in paleoclimatological data, however, stems from what Christian Pfister has called the archives of nature. These are organic or inorganic phenomena whose growth or composition in time is correlated with changes of temperature, precipitation, and other factors, and thus can be used as proxies for these parameters. These proxies differ regarding their spatial and temporal coverage, which may range from microregions to larger areas and from sub-annual resolution to millennia. One telling example are tree rings, whose varying diameters, depending on local conditions, reflect changes of temperature and/or precipitation. More recently, equally the isotope composition of these layers has been analyzed for further reconstructions of hydroclimates of the past. Along similar lines, the deposition layers of speleothems, dripstones, are used for the reconstruction of precipitation conditions, as in this example from the Sofala cave in northwestern Turkey for the last 3,500 years. Sofala also appears on this map of proxy sites in the central and eastern Mediterranean, which was created for a joint paper under the leadership of the paleoclimatologist Elena Xoblaki. While the density of data for some regions is impressive, we detect large spaces uncovered by such data in a fashion similar to the unequal distribution of historical archives of society. Tree rings, for instance, come mostly from higher altitudes and/or higher latitudes, as this map from a recent study on the impact of volcanic eruptions on climate variability in the Common Era illustrates. Furthermore, the number of available datasets decreases when going back in time, affecting a larger margin of error for temperature or precipitation reconstructions for earlier centuries. In addition, these unequal spatial and temporal distributions complicate reconstructions of climates of the past for larger areas or at a global scale. As this map from a recent study of Raphael Neukomm and his team illustrates, deep ocean basins, which play a decisive role in global climate dynamics, are for instance thousands of kilometers distant from the next proxy data sites. In short, scientists of the climate of the past encounter similar interpretative problems with their data as historians do with their sources. Therefore, specialists for the respective archives of society and of nature need to collaborate at eye level to bring together the different sources for reconstructions as nuanced and well balanced as possible, also clarifying their margins of error and uncertainty. As I've mentioned before, from this follow more and more complex descriptions that make a clear periodization of climate history, as preferred by both scholarship and wider public, more and more tricky. This graph shows a recent reconstructions of average summer temperatures in Europe for the period between 100 BC and 2003 CE based on tree rings. The clear ups and downs of Lamb's graphs from the 1960s, or even still of the reconstruction of Northern Hemisphere temperatures of 2005, are gone. Even if we concentrate the data into 100 years moving average, nothing like the more coherent episodes that we have labeled as late antique cold period or medieval warm period shows up. They are replaced by several hills and valleys, some of which have received their own labels in recent years, such as the since 2016 so-called late antique Little Ice Age Lalia between 536 and 660 CE. Furthermore, as Raphael Neukomm and his team have demonstrated, proxy datasets are not only highly unequally distributed across time and space, but they also tell different stories of the actual regional manifestation of global climate trends. Thus, there was nothing like a chronologically coherent medieval warm period or little ice age across the entire globe at the same time. Only the current warm period shows a remarkable temporal and spatial coherence over the entire planet in contrast to all earlier episodes of climate history of the last 2000 years. The medieval warm period identified by Hubert Lamb for England turns out to be a valid label only for northwestern and western Europe. Climatology therefore has mostly switched to the term Medieval Climate Anomaly, which is with its various regional manifestations. Equally mainly from a perspective centered on Western Europe stems the term Medieval Climate Optimum, since beneficial temperature and precipitation conditions would have favored the expansion of European societies in these centuries in the form of the Viking settlement in Greenland or the Crusaders' conquest of Jerusalem and adjacent regions in the Levant. As I have mentioned before, such an interpretation raises a cheer among the deniers of anthropogenic climate change, in some cases both in terms of their environmental and cultural political agendas. As a matter of fact, one finds correlations between climatic parameters and indicators for the demographic and economic growth in Western Europe between the 10th and 13th century, such as the numbers of foundations of new settlements and towns or of religious institutions. Signs of renewed expansions of settlement and agriculture after the decline of the late and post-Roman period, however, can be found in archaeological evidence and pollen data in various regions since the 6th century CE, that is already before the climatic trend reversal towards the medieval climate anomaly, such as for areas in today's Netherlands and Belgium, parts of southern Germany, today's Lower Saxony, Brandenburg, or the northwest of Poland or England. This dynamic increased in the 7th century and continued until the 9th century, with new forms of cultivation and technical innovations playing a role. Political instability and other factors, on the contrast, impeded such dynamics in some of these and other regions even after potentially more beneficial climatic conditions had set in from the 9th century onwards. Against linear models, climatic conditions per se were a relevant but not sufficient factor to initiate growth. Furthermore, large-scale climatic oscillations, such as the infamous El Niño Thousand Oscillation, induce different trajectories of macro weather situations even in neighboring regions. For Western Afro-Eurasia, the Northern Atlantic Oscillation, NAO, plays a decisive role. Its dynamics are measured in an index of the differences in air pressure between the Iceland low and the high over the Azores. A high difference between these air pressure regions, resulting in a positive NAO index, usually causes warmer and wetter weather in Western and Central Europe, but drier conditions in the Mediterranean. A low difference, on the contrast, results in colder and drier weather in Western and Central Europe, but more humid conditions in the Mediterranean. For the most stable periods of the medieval climate anomaly, a predominantly positive NAO index was reconstructed. In the Mediterranean, however, a further seesaw of precipitation conditions was identified between the west and the east of the basin, with the former often affected by more arid conditions during the medieval climate anomaly, while the latter sometimes experienced more humid ones. Thus, even across medieval Europe and the Mediterranean, nothing like a coherent medieval optimum can be identified. The notion of such an optimum, however, was not only developed for Europe, but also for Southeast Asia, for instance, by specialists on the region such as Victor Lieberman. Among other aspects, he referred to the already mentioned El Niño Southern Oscillation, which usually brings dry conditions to Southeast Asia. According to paleoenvironmental reconstructions, the frequency of such El Niño events declined during the medieval climate anomaly, which together with other parameters would have contributed to a more beneficial climatic conditions in the region. Thus, Lieberman wrote in his first volume on the strange parallels of developments in Southeast Asia, Europe, and other parts of Eurasia in 2003, quote, "I do suggest that unusually favorable climatic conditions between 1000 and 1300 helped to jumpstart Southeast Asian and other Eurasian charter civilizations, creating in each locally a richly innovative substratum, economic, cultural, institutional, on which subsequent generations would draw heavily to resume expansion in less favorable climates." However, in the same volume and even more in the second of 2009, Lieberman introduced some caveats, stating, in my view very correctly, that global climate change rarely, if ever, yielded uniform effects across Eurasia. Furthermore, he wrote that climate change was always mediated and partly masked by social, cultural, and technological factors. In addition, since the publication of the second volume of Strange Parallels in 2009, as for other areas, also for Southeast Asia, an increasing number of more detailed proxy data has very much modified the scenario of a coherent, optimal medieval climate anomaly, replacing it with regionally diverse fluctuations between more humid and more arid periods. In general, to do justice to the complex interplay between climatic change, regional ecologies, and human communities, we have to get beyond linear correlations between climatic and socio-economic trends. Environmental historians and settlement archaeologists such as Rainer Schreck for a long time have argued for more elaborate models which integrate both climatic dynamics as well as human agency as factors among others in a complex web which entangles social systems and ecosystems. Ecologists have identified similar networks between physical environments and species across scales from microhabitats to macroregions. And the new discipline of climate change biology, which explores the impact of past and current global warming together with human activities on these networks, provides further hints for a more nuanced perspective on socio-ecological dynamics of the past. Medievalists such as Jamie Greiner in her magnificent recent monograph on pigs in the early medieval West have pointed out that such an entangled ecological thinking was not alien to both medieval farmers as well as scholars. Such studies also help to put into perspective the still circulating ideas of the US historian Lynn White Jr., who in 1967 tried to find the historical roots of our ecological crisis in the Middle Ages. Referring to Genesis 1:28, where it says, "Be fruitful and multiply, fill the earth and subdue it, and rule over the fish of the sea, over the birds of the sky, and over all animals that crawl on the earth," he argued that the exploitation of nature was programmed from the start into Christianity and the medieval societies influenced by it. Immediately after White's essay was published, various scholars noticed that pre-Christian and non-Christian cultures exploited nature no less than the medieval societies of Western Europe did. And while Christianity certainly played an important role in the understanding of nature in Western Europe, a closer examination of the interpretation of the Genesis passage in the Western Middle Ages revealed that it was by no means only interpreted in the way White had assumed, as also Jamie Greiner demonstrates. Nevertheless, we should be aware of the impact human agency had on existing ecological networks, such as food webs or pollination webs, even in the absence of anthropogenic climate change or ahead of modern industrialization. As the examples on these slides from various maritime habitats demonstrate, humans dramatically altered ecosystems, putting themselves into the center of a modified and often reduced constellation of species, some of which went extinct due to the loss of their habitats and nutrition bases. Most recently, Adrian Newton, in his monograph, and Stephanie Crabtree, Stephanie Dunn, and Spencer Wood in their illuminating paper have demonstrated how such analysis can be applied on societies in the more distant past. While ecosystems, especially since the introduction of agriculture, but already before, were always fundamentally modified by human action, the new entanglements between humans and native, imported, wild, and domesticated species did not necessarily result in environmental degradation. Balances between landscape and its usage, however, became more delicate and potentially more vulnerable to additional pressures such as climate change. For the medieval period, such phenomena can be observed most clearly when settlers arrived in ecosystems mostly untouched by human activity before. During the medieval climate anomaly, we find such cases within larger-scale maritime migration movements on two opposite places on the planet. The settlement of Polynesians on New Zealand around 1200 CE and the so-called Landnam of the Vikings on Iceland in around 870 CE. As proxy data indicates, the arrival of both groups took place during respective warm periods in these generally more temperate or even cold zones. The arrival of the population eventually becoming the Maori fundamentally altered the fauna and flora, especially on the northern island of New Zealand, by hunting, gathering, and growing of various crops they brought with them from their places of origin. Most probably, overhunting led to the extinction of several species, such as the huge Haast's eagle and the massive moa ratites, and a significant modification of food webs. As pollen analysis indicates, fire clearing for shifting cultivation and lumbering led to deforestation, with 40% of the forests on the northern island gone within 200 years after the arrival of the settlers. This was the most dramatic event in New Zealand's Holocene history, in its enduring effects outperforming earlier more dramatic episodes of climate change than the medieval climate anomaly, such as the end of the last glacial. Based on pollen data and other paleoenvironmental analysis, similar observations have been made for Iceland. Overhunting led to the almost extinction of the local walrus populations, whose tusks in turn became an important export product of North Greenland, where walrus populations were more abundant. Fire clearing and lumbering induced an almost total disappearance of Iceland's forests, especially of birch, within 50 years after the Landnam of 870. Although major volcanic eruptions time and again had contributed to a massive modification of landscape, after the last glacial, and before the human arrival, flora and fauna had recovered from such extreme events within a few decades. Now, in most parts of Iceland, regional ecologies entered a totally new constellation with the arrivals from northern Europe as main movers. In contrast to the still popular narrative of Jared Diamond's book of 2005, which especially referred to North Greenland, however, the result of these settlement projects during the medieval climate anomaly was not collapse, but the emergence of new, sometimes fragile, sometimes relatively resilient, anthropogenic ecologies. For Iceland, recent studies suggest that the loss of 90% of the original forest cover and 40% of the soil due to erosion was not only due to the exploitation by the settlers, but also due, and in combination with, climate changes and geological processes, especially the regular large volcanic eruptions. On the contrary, some farmsteads and smaller settlements in the interior were apparently abandoned in a planned fashion to protect the surrounding woodland from further overuse and erosion. In other areas, the Icelanders' agriculture increased soil fertility, and the introduction of new species increased biodiversity, which partly benefited the ecosystem. Nevertheless, life in the North Atlantic fringes remained precarious, especially when climatic conditions deteriorated from the late 13th century onwards towards the Little Ice Age. From the 1260s-80s, cooling set in, intensifying from 1320 onwards, and in 1370 leading to the coldest winter since the Landnam 500 years before. In contrast to Greenland, however, where contacts between Scandinavia and the Norse settlements dwindled at the time until the later were abandoned in the early 15th century, Iceland's economy profited from an even despite the Black Death intensified interest of mainland Europe due to the growing demand for its fish, especially dried cod, in cities not only in northern Europe but also in the Mediterranean. This intensified use of the fishing grounds around Iceland, however, must have considerably modified the marine ecosystem there, as the findings of ecological network analysis, which we have discussed earlier, suggest. The fact that the fishing fleets from northern Europe were advancing further and further into the North Atlantic was already a result of the decline in stocks in the waters closer to the mainland coasts. As Richard C. Hoffman and others have demonstrated, this was due on the one hand to overfishing to meet the increasing demand in urban markets across Europe, and on the other hand due to climatic changes of the 14th and 15th centuries. The herring fishery broke down off the east coast of England between 1316 and 80, and in the early 15th century that in the Öresund between Denmark and Sweden. From the middle of the 15th century, the new fishing grounds of eastern Scotland also produced fewer yields when particularly cold and stormy conditions during the solar spura minimum not only hindered shipping but also reduced the chances of survival for the herring larvae. In search of new fishing grounds, Flemish, Dutch and English fishermen, some in partnership with Italian financiers, penetrated further and further into the North Atlantic in the late 15th century, not only into the seas around Iceland, but ultimately further west into the area of Newfoundland on the North American coast. These developments illustrate the manifold ecological effects of the growth period connected with the medieval climate anomaly in Western Europe, resulting in further episodes of the expansion of the metabolisms of Europe's societies. This concept stems from the field of social ecology, which focuses on the specific flows of materials between nature and society in forms of inputs, resources, and outputs, waste, on which the preservation and reproduction of human communities depend. Hotspots of such metabolic processes were and are larger urban settlements, with the concentration of population, production, consumption, and pollution. As Dieter Schott explains, if cities and their population grow, they will need to reach beyond their immediate surroundings in order to fulfill their basic needs. They will tend to exercise either political dominance by extending the territory they control or use market power to attract production surpluses from further distant regions. Thus, cities mobilize in a variety of ways resources of an ever-widening hinterland for the social metabolism. Doing so, they frequently transform even remote ecological systems of these hinterlands, for instance, by lowering the water level through large-scale water extraction, by deforestation, by polluting rivers and dumping urban wastes on dumps and sinks at a distance from the city. At the largest scale, ancient or medieval megacities depended on the flows of people and material of an entire empire. What the environmental historian Sam White, for the case of the Ottoman Empire, has called imperial ecology. Among such imperial centers which emerged and flourished during the medieval climate anomaly, one may think of Cairo in Fatimid Egypt or Kaifeng in Song China. These places provide telling examples for the interplay between long-term climatic and socio-political trends, economic and demographic growth, and the accumulation as well as unequal distribution of risks during the medieval climate anomaly. Based on an increasing number of proxies as well as rich historical source evidence, a medieval climate anomaly also for China has been identified as a period of often potentially beneficial climatic conditions, especially during the rule of the Northern Song dynasty between 916 and 1126. The number of households recorded in the text registers more than tripled during these 160 years. Kaifeng became a megacity of more than 1 million inhabitants, whose supplies depended on an elaborate and cost-intensive canal system, via which surpluses from the provinces along the Yellow River, as well as the Yangtze, were transported to the capital. Along the Yellow River, however, the expansion and intensification of agriculture, together with deforestation, dramatically increased the risk for major flood events and dam breaches, especially in the case of heavy rainfall. The frequency of this and other calamities increased in the 11th century during the so-called Oort minimum of solar activity. Even such minor reductions in solar irradiation can contribute to perturbations of existing climatic patterns, resulting in various forms of extreme events depending on regional atmospheric dynamics. During the Oort minimum between 1020-40 and 1080, such catastrophes were not only reported in China, but also in the Byzantine Empire, Central Europe, Fatimid Egypt, the Middle East, or Central Asia. In Song China, the fatal combination of increased vulnerability to flooding and heavy rainfall in 1048 led to massive dam breaches, huge floods, and a catastrophic shift of the entire lower course of the Yellow River into the province of Hebei. Hebei already before had suffered due to its position at the frontier to the most dangerous rival of the Song, the Liao Khitan dynasty, who ruled over Manchuria and parts of northeastern China. After an invasion of the Liao in 1004, not only numerous garrisons generated a heavy tax burden there, large areas in the north of Hebei were transformed into artificial lakes as obstacles for the cavalry of the enemy. Now after 1048, Hebei was cut in two by the shifted Yellow River, and to protect Kaifeng from floods, dams in the following decades were opened several times on the northern banks of the Yellow River to release dangerous water masses again into Hebei. Within the socio-spatial power arrangement, Hebei became the expandable part of the Song Empire during a period otherwise described as time of prosperity, as Ling Shang, who also gave a keynote lecture yesterday, describes in her masterful monograph of 2016. In the 1070s, however, a group of more interventionist dignitaries led by the scholar Wang Anshi convinced Emperor Shenzong to undertake efforts to redivert the Yellow River in its old stream bed before the catastrophe of 1048. These building measures proved ridiculously expensive but ineffective. And in 1070-78, when after another series of heavy rainfalls, the water masses of the Yellow River again threatened the capital, once more dams were opened to the north, and Hebei devastated by floods, as the contemporary author Hung Ting-jian describes. This environmental drama, as Ling Shang has called it, illustrates that the actual impact of climatic fluctuations cannot be understood without the analysis of pre-existing political, economic, and ecological arrangements and the patterns of cognition and tradition that underlie decision-making within a society. These frameworks are ultimately decisive for the actual outcome of such crises on the local, regional, and polity-wide level. Another such interplay between long-term trends and short-term shocks can be observed for the medieval Roman Empire of the East, commonly known as the Byzantine one, in the 10th and 11th centuries. This period is usually identified as the heyday of the empire, which under Emperor Basil II between 976 and 1025 ranged from the Danube to the Euphrates. Contributing to and in turn profiting from this process of securing and expanding the imperial borders was a renewed expansion of agriculture in Asia Minor, starting in the 9th century, as Adamit Stepsky and his team have demonstrated based on synthetic pollen data for various regions. A similar period of agricultural growth started in Greece from 900 onwards. In addition to improved security conditions after centuries of Arab raids, climatic parameters may have contributed to this economic expansion. Data from the sediments of the Techergöli and Nargöli in central Anatolia show a trend towards more humid conditions after a dry phase in the early 9th century. In the early 11th century, the material flows of the imperial ecology from southeastern Europe and Asia Minor supported the renewed growth of Constantinople, which maybe reached a population of up to 200,000 people after the nadir in the aftermath of the Justinianic plague of the 6th to 8th centuries. Yet, within 50 years after the death of Basil II, the empire was torn by civil wars and threatened by foreign enemies in the Adriatic, at the Danube, and in Asia Minor, where the Seljuks and other Turkmen groups occupied most of the former core provinces. By 1081, Byzantium seemed at the brink of collapse. This swift reversal of fortunes has puzzled both contemporary authors as well as modern scholarship. In his monograph of 2012, Ronnie Ellenblum had argued that the almost collapse of Byzantium, together with other crises in politics of the Middle East, such as in Buyid, Iraq or Fatimid Egypt, are connected and should be understood within the broad context of climate change. He was referring to the series of weather anomalies during the odd minimum. However, as I demonstrated in a paper of 2015, as well as in my two most recent monographs, a closer examination of various proxy data, as well as written evidence, indicates strong regional differences regarding atmospheric effects, as well as the socio-political processing of environmental challenges. Neither was there a ubiquitous climate catastrophe nor a general collapse in the eastern Mediterranean of the 11th century. Unfortunately, Ronnie's untimely death in January of this year prevented the continuation of our heated but friendly debate, and I would like to devote my lecture to his memory. Rather than the short-term weather shocks of the odd minimum, it was the unequal distribution of the fruits of the preceding growth period which contributed to a destabilization of the Byzantine Empire. It enabled several powerful elite families, especially in Asia Minor, to increase their influence until the competition for the imperial throne erupted in a series of fatal civil wars, preceding and then amplifying the effects of the defeat against the Seljuks and other enemies. This rather traditional position of Byzantine scholarship has been challenged recently by Anthony Kaldellis, who argues that the civil wars of the late 10th and 11th century should be attributed to the usual fragility of imperial power and not to new socio-economic dynamics. In contrast to the narrative patterns of Byzantine imperial history on which he bases his narrative, he considers the descriptions in imperial legislation of this time, which draws a different image, as largely rhetorical and inaccurate. However, although these law texts represent the biased perspective of the central imperial power, I am not convinced that the socio-economic phenomena they describe regarding the expansion of the property and power of the so-called dynasty to the disadvantage of smaller-scale landowners should be regarded only as rhetorical devices. Even more, since Emperor Basil II connects them to his own observations during campaigns and travels in Asia Minor. As countermeasure, he was extending a helping hand to the poor in every way in checking the excessive power of the dynasty, a matter best treated long ago by our blessed great-grandfather, the Lord Emperor Romanos the Elder, in the alienation of the immovable properties of the weak to the dynasty. Here Basil II was referring to the first of these laws against the encroachments of the dynasty issued by Emperor Romanos I Lakapinos in 934. Romanos I in turn identified a climatic anomaly 7 years earlier as cause for an intensification of the power shift in the countryside. The extreme winter of 927-28, which is also described in Syriac sources for Iraq, was followed by a cruel famine. As we learn from the law issued by Romanos I 7 years later, the dire situation of small and medium-scale landowners, whose supplies ran out during the time of need, allowed the dynasty to buy the properties of their poorer neighbors at low prices. Therefore, the emperor ordered that land sales, which had taken place in the aftermath of the winter of famine under these exceptional circumstances, should be undone. We do not know how effective the imperial legislation was in the provinces. The repeated issue of similar laws by the successors of Romanos I until the reign of Basil II suggests rather limited success, even more so since this process was also carried by dynamics from below. That is, farmers preferring to sell their land to powerful elite neighbors and to work for them as tenants, in order to profit from their protection and resources in cases of political unrest, or, as in the aftermath of 927, of crop failures and extreme events. We may assume that this long-term trend started in the late 9th century, intensified with the imperial and economic expansion of the 10th and early 11th century, and heated up in the aftermath of short-term shocks, such as in 927 or during the odd minimum in the 1020s and 30s. As Aramid Stepsky, Lee Mordechai, and Sam White have pointed out, the winter of 927-28 teaches us several interesting lessons. First, about the limits of the archives of nature, since no currently available paleoclimate proxy confirms the occurrence of a strong winter cooling or at least a potential increase in snowfall at the time of the winter of famine. In contrast, we have the perception of the contemporaries and the later interpretation in Byzantine historiography, where the long winter was thus used as a way of understanding the reasons for the social transformation, as it accelerated this process and brought it to contemporaries' attention. In general, the environmental stressor, even if in physical terms it was not the harshest winter of the 10th century, impinged upon the complex web of crop ecologies, social relations and the state's interests. Thus it added new momentum to the extant social dynamic, that of office-holding elites, accumulating wealth that allowed them to become an increasingly powerful social group within contemporary Byzantine society. As in the Chinese case of Kobe and the Yellow River, we learn about the short-term costs and long-term effects of recovery after catastrophe and the unequal distribution of these costs. From a broad perspective, then, Byzantine society proved resilient, surviving the crisis caused by the long winter of 927-28. When seen from the point of view of specific social groups, however, the price for this resilience was a significant shift in the balance of socio-economic relations. To proceed further beyond the macro perspective of the entire Byzantine Empire, as for Chobe, we need more research on the regional diversities of this interplay between agricultural growth, socio-economic power shifts, long-term climatic trends, and short-term extreme events on the ground in the various provinces. Already in 2001, A.T. Grove and Oliver Rackham, in their book On the Nature of Mediterranean Europe, had synthesized findings on episodes of intensified erosion and sedimentation from areas on the Peloponnese and Crete in the medieval period. Further studies have followed and some suggest that, at a smaller scale, but somehow like the Yellow River in China, a combination of intensified land use in the centuries of agricultural and demographic growth, with episodes of extreme precipitation, snow or rain, during climate anomalies such as the Oort minimum, played a role in these significant changes of landscapes. On the other hand, we may ask if we find signs for political and ecological crisis of growth during the medieval climate anomaly in other societies than Song, China, and Byzantium. Japan may be a comparative case where the unequal distribution of the fruits of growth contributed to a power shift towards landholders in the provinces and ultimately the emergence of a rule by the warrior class with the establishment of the shogunate in 1192. For Western Europe, Thomas N. Bison has suggested similar dynamics during the 11th and 12th centuries. This brings us back to the narrative about the medieval climate optimum and the question when and how a climatic trend is beneficial, and for whom. As I hope to have demonstrated, the multitude of proxies, the diversity of regional dynamics, and the multiplicity of narratives frustrates any simple answers to these questions. Within the time slot of this lecture, I was able only to refer briefly to some selected examples. You will find more on these and other case studies from Europe, the Mediterranean and the Middle East in my recent monographs, unfortunately only in German at the moment. In general, one cannot deny that our interest as historians of the 21st century in the climate history of the Middle Ages is motivated to a significant extent by the current debates on global warming. If we combine the most elaborate concepts and methods of ecology and environmental studies with traditional critical evaluation of our evidence, we get beyond simplifying scenarios of climate-induced fluorescence or collapse, as they also derive from a naive application of terms like Roman climate optimum or medieval warm period. Such a history of climate and society, as also outlined most recently by Dagomar de Groot and his co-authors, will lend itself not easily to political misinterpretation and ideological abuse from whatever direction. On the contrast, it may help us to understand the dynamics of social and environmental change, of varying ecological and economic vulnerabilities as emerging from power differentials within and between societies, and how even in a globalized world, the one universal challenge of climate change and species extinction will demand and provoke a multiplicity of answers and reactions as it did during the Middle Ages. Thank you very much for your attention.